Okay, it's week 2. We'll try to have another little bit here and see what we can learn in the coming week. You noticed that the first week you really talked just about the atmosphere as a whole, and then we went into temperature and the energy that comes from the sun and what really makes the atmosphere begin to move around and begin to spin uh, and begin to cause our weather. Well, now we're going to go into another couple elements of the meteorology side of it. Atmospheric pressure. Well, that's really the weight of the air at any one location. We all feel it every day, even though you don't notice it. If you go up on top of a mountaintop, it's not nearly as much pressure on you. I always found it interesting when I was out in the Rocky Mountains for some classes that when I went on top of some of the 12,000 foot elevations out there, and there was a 40 and 50-mile-an-hour wind blowing in my face, and it was like nothing. However, if I went down on the ground and had that same wind blowing in my face, and it would have been almost knocking me over. So it was very interesting to feel the differences. The first thing we talk about here is pressure gradient and how the pressure wants to even everything out. Everything nature would just like nothing better than all the pressures to be exactly equal, all the temperatures to be equal everywhere. But because of the way our Earth is, that doesn't happen. So it's always trying to work towards that. So everything it's doing on the pressures, on temperatures, is trying to equalize it all. So the first thing we talk about pressure gradient in the vertical, literally, which is the hydrostatic equilibrium. Uh, all that is yes, the pressure decreases with height. So you would think that the air would try to move upwards, but you have gravity holding it downwards. So you wind up with an equilibrium where the air is being held down by the force of gravity and the pressure gradient trying to work in the opposite direction. So you wind up with the air very much just staying where it is. There are different instruments to measure pressure. Mercurial barometer, when I first came into weather service, we used that. It literally was the standard we used everywhere we even went to airports to check the barometers out at various airports. I had to conduct surveys, and we always took the mercurial barometer with us to verify exactly how theirs was operating and if they were within specs. It's always an interesting thing. One of the big keys on pressure is you've got to have it at sea level. Uh, as much as we would like to simplify the process and say, oh, the pressure could be wherever that elevation is, it's just not going to work. That's why sometimes, for example, out in the Rocky Mountains, at 850 millibars, which is up, a little bit into the atmosphere at about 5,000 feet to a little more, is actually going to be into the mountains. So you don't really want your pressure in the mountains. It doesn't work too well. So you really need to know be able to reduce the pressure down to from the mountaintop down to the surface, so you'll actually have a good understanding and be able to have everybody on the same surface for your weather maps. We're going to look at some of those weather maps here later on. And here's an example of a surface pressure pattern. This was back uh, during the winter time. You can see there's a fairly strong high out in the mountains, and you can see how messed up it looks out in the mountains. It's because the reduction to sea level isn't perfect. Uh, it's good, but it's not perfect, and the mountains mess up the pressure. So you can see there's like a high sitting over eastern part of Washington State, and another high down over Idaho, and even bridging down right along the mountain chain there, probably on the eastern slopes of it, between the Rockies, which would be to the east, and the Sierra Nevadas, which would be to the west. So you can see that, because we're trying to reduce it to sea level, we're not always getting the perfect picture when the real high mountains. However, when the country starts flattening out towards the plains and most of the rest of the country, we're getting a pretty good estimate. You can see a low pressure here over part of Oklahoma and down with a cold front. The kink in the isobars will be along a cold front typically, or a kink in the isobars might be along a warm front. And you have another strong low pressure up over north of New England as well. So just some things to look at on the weather map here. Here's an 850 millibar chart. And you're up about 6,000 feet in the atmosphere. This is a great chart to look at to see where moisture is going. And we'll get into moisture in week 3. But for right now, just know that it really can affect your atmosphere a lot. So you can see a moisture plume coming up from the Gulf of Mexico right here, across Texas and into Arkansas there. And it's all being pulled north by this low. And we saw a low at the surface. The low at the surface was actually east of the 850 millibar low. You're going to find that when you look aloft on weather maps, they all tend to slope back towards the cold air. So the surface lows are further east typically, while the other ones are further to the north and the west. And you can see that looking at the flow of the winds around it there, you have good warm advection to the east side of the low, and you have cold advection. You can actually picture it, and we talked about that last week, coming to the other side. One of the things as pilots, you need to be understanding how these things might change. And if you're flying around, you can actually maybe pick up some clues from the winds you're picking up aloft that you're observing, maybe from the amount of clouds. Maybe they can tell you whether the forecast is good or whether it's just not going right. And by knowing where you may be able to deviate from that, it can help you avoid some major issues. We talk about pressure altimeters this chapter, and some of the areas, a lot of the areas are going to be caused because we're not dealing with a standard atmosphere. Almost never are we dealing exactly standard. So there are going to be errors in it. And even some strong vertical motions can cause some errors, particularly during thunderstorms or mountain waves. Saw in the discussions this week, we were talking about some mountain waves. They can really add up very quickly into very strong vertical motions, both up and down. Density altitude is something you're going to be discussing. Again, the simple equation, pressure equals density times temperature times a constant R. And from that equation, you can actually say, okay, well, the pressure might change and temperature might change. You can actually see the magnitudes of how much things may be off, how your density will compare to the pressure and temperature. So say you were in the middle of summertime and you had a very hot, humid air mass like we're talking about here. Your density is going to be quite low compared probably to the standard atmosphere. It's going to take you much longer to run out and get up in the air than it would otherwise. By the same token, if you're up further north, maybe in a cold, dry day in the middle of winter, the air is very dense when it's dry and when it's very cold, and that's going to change how your density is going to work as well. One of the things that's always interested me is during the summertime, particularly, you get very much solar radiation on mountaintops. So say you have a mountaintop airport, and maybe down in the valley, yeah, it's maybe 90 to 100, but it might be the same temperature almost at the mountaintop, 90 to 100. So you're already starting out with a lower pressure. Your temperature may be the same, but your pressure is lower. So your density is going to be significantly lower as well. So maybe you have to take that into account as well, planning how things are going there. We'll look a little bit too at the week after that coming up here in a minute, but so let's look at winds here. Winds come right out of pressure and the density changes. You think about the atmosphere, and we've talked about temperature already. We've talked about pressure and density. Well, now we're going to talk about winds. Winds are two components. It's a vector. So you have speed and direction. So every wind, we divide them as a meteorologist into a U component and a V component. A U component is truly east to west. A V component is north to south. When you combine them together, you get an actual wind direction, which is some other direction typically than either east or true west. So it's a vector. It means it has both a speed and a direction. This is a typical ASOS sensor. I just grabbed the picture. There are most airports, either ASOS or AWOS. AWOS is very popular nowadays. It's just another form of automated sensors. ASOS measures sustained winds. in an increment of every 2-minute average. So it takes the wind, averages over the 2 minutes. It also finds the gust, which is the maximum wind speed, in the last 10 minutes. It can even do a peak wind if the wind's high enough over the maximum speed in the last hour. One of the nice things about ASOS is ASOS literally can take readings almost every second. Typically within every minute there's a reading that can be broadcast, so that if things are changing quickly, you're getting a lot of specials, a lot of important observations out there from ASOS, which can help determining keeping you safe out there. Winds are really, they come down to Newton's laws of motion, but the simplest one that he uses here is just to state that unbalanced forces will cause something to undergo an acceleration. In the aircraft, if you start your engines up, get them moving, they're going to push your aircraft forward. That's an unbalanced force. There's a force from the engines against you just sitting still, so you've got to be moving somewhere. If you had your brakes on, you're not moving, so you now have a balance of forces. So you have two forces acting against each other. The same holds with air parcels. You have air pressure, which is pressure gradient force. Basically, that means pressure is going to want to go from high to low. Think of it as mountains to valleys. The air is going to want to flow down from the mountaintops in high pressure and into the valleys in the low pressure, and they're just going to want to keep it that way. So that's what they're going to be trying to do. Anywhere you look at a weather map, that's the first thing you're going to see, is air pressure is going to force winds to go from a high pressure towards low pressure. The next force to act on it is the Coriolis Force. If you ever think about the Coriolis Force, it's just a spin of the Earth causing the air to kind of change the direction. It's always, in the northern hemisphere, always will turn the air parcel to the right. So if you have a southerly wind, you would be gradually turning that southerly wind more to the east with time. If you have a northerly wind, it's going to gradually turn that more to the west with time. And it's a slow process. For example, if you have a tornado develop, a tornado may only last a few minutes. In the northern hemisphere, typically, because of the Coriolis force, low pressures always have counterclockwise circulations around them, and high pressures have clockwise circulations around them. Well, and it's a very strong low pressure in the middle of a tornado. However, because of the tornado only lasts a few minutes, it takes time for Coriolis force to act. It doesn't act real quickly. So that will mean that you can't actually have a clockwise rotating tornado in the northern hemisphere. It's a very rare moment, but they do occur, just because the Coriolis force hasn't had a chance to act yet on that flow of air. And then there's another force that typically comes into play, and that's the frictional force. You think about friction, you think about wind over water, and there's not much friction there. The water just kind of plays with it a little bit with the waves. But if you took that same wind, put it over land, it would be very rough. It would tend to slow down that wind. So friction has a big role and can be very different depending on whether it's over a very flat terrain or very rough terrain, over water versus land. There's changes in friction. If you ever look at the air speeds, when you go from, say, the Great Lakes, the wind blowing across Lake Erie, you'll see one speed over the water. Once it hits the land, that speed is going to go down. It's going to decrease. So that's just the fact that the friction forces on that, how that's acting. So when you put all these forces together, you're going to start balancing everything out. One of the things it talks about the thermal circulations here, such as the sea breeze. Sea breezes can occur anywhere from large rivers, even over lakes, to over the oceans. All it really requires is the temperature over land is getting warm. The temperature over water is staying relatively cool. Think about it. Over land is getting warm, your temperature is getting higher, and your pressure is going to begin to drop. And when that happens, air from the water begins to flow in, and air aloft, where you have the higher pressures from the air moving up, is going to flow out back over the water. So you wind up with a circulation. It just reverses itself at night. Coriolis Force, again, it's going to be strongest really at the North Pole, where the Earth is not spinning as much, actually, as the equator, where it's spinning the most. But you have no Coriolis Force at the equator. The Coriolis Force does not change anything at the equator. And this actually has an impact on low pressure systems around the equator. They just don't form there much because of that. There's no Coriolis Force to cause the winds to turn around in a circle to make a low pressure system. However, they will form at the North Pole. So the geostrophic balance is just the first part of the equation. All it's taking into account is, let's go back on this slide a second here. Just the pressure gradient force and the Coriolis force. So when they get into balance, what you wind up doing is wind up having the flow parallel the isobars. Or if it's a loft, it's the contours. We're looking at, say we have an 850 millibar surface we want to look at. Well, the pressure is exactly the same all along that surface. So it's just the height of that 850 millibar surface that you're measuring. And that can measure up or down depending on how the pressure changes at that level. And by looking at the height, you're literally looking at how like a pressure isobar chart from the surface. So you can actually see that. We're going to look at some of these charts in a little bit. And then, of course, friction, again, as the mountainous terrain, as you go across more and more friction. And the friction is going to tend to slow the wind speed, but also will, by slowing that wind speed, it's going to tend to want to come back into geostrophic balance, and the wind will kind of tend to move towards low pressure. So that when you look aloft, you'll see higher wind speeds, less friction, and winds will tend to be more to the right. They'll veer that way. The boundary layer is where all this mixing occurs. We're going to look at soundings in detail later on in this course, and they're going to help you understand some of this better. But think of the boundary layer as being just a well-mixed layer. It's an area in the atmosphere that is mixed totally from the surface to that top of that layer. And the temperature, because of that, is going to be decreasing very typically at the dry adiabatic rate quite often, which is, again, something we'll talk about more down the road here. So with that in mind, let's look at some of these maps here a little bit. So let's start off with a surface map. Today's surface map, I'm on a Thursday. It may not be the same for you, obviously. But looking at the pressure gradients, let's take a look here. We have a very strong high pressure over Canada right now. To the point in millibars, it's a 1044 high, maybe even above 1050 if you went far enough north into Canada there. So if there's a pressure gradient from that, high to low, you would think, okay, all the winds would be coming straight due south out of that low, right? Well, again, we have that Coriolis force trying to act things to turn to the right. So instead of that way, they're kind of turning around. Here you have trying to blow through and around the high to make a clockwise circulation. But you'll notice that the stronger the pressure gradient, the more across the isobars, the more what we call ageostrophic the flow becomes. So the stronger the pressure gradient, the better tendency that the air is going to try to really flow from high pressure to low pressure. And you can see that up here in this part of Canada. We have a very nice cold front well stretched across the country here, and another low pressure system up north of New England, pushing that low through. Again, you can see the flow around it. But friction and stuff is all causing the air to come inwards here as well. Have a nice high pressure sitting over the southeastern states, and you can see winds around, rotating around that high. The pressure gradient force is not nearly as strong on this, so they're not trying to cut across the isobars as much here, maybe as they would with the pressure gradient is much stronger up here. So let's look a little bit now at the same chart, just see how it changed like 12 hours ago. And 15 hours ago, you can see that the high was further north, front was not as far to the east, and no pressure there. There's just some differences in it, how it's moving around. So we're going to take, well, I try to pick areas to fly through or whatever with this. It's a little tough on this one. I'm having trouble trying to figure out where I'd like to fly from too, I could just make it simple and go right across this frontal boundary again. But maybe we'll look at a storm later on and maybe take a prediction on where we'd like to fly through in the future. So let's take a look at a couple upper air charts as well. These upper air charts, we'll start with 250 millibars. Again, you're looking at contours here. The contours are solid lines. What you're seeing shaded is wind speed. So the stronger the wind speed is where the shading is different color. And you actually have here, this is where the jet stream runs, basically, about 250 millibars. It's really a good level to take a look at the jets. What do you see across the United States? At least what I see real quickly, just looking at it, is a very strong flow from the west to the eastern part of the United States. 100, 150 knots of wind up in here. So it's pushing in very fast from the west coast. Very strong jet streak right in here across Washington, into Idaho, into Montana there. So there's really good upper level energy right in here. You also have another little feature down here off the southwest coast of the United States into Mexico even. Almost like a low pressure at this level, and a little bit of a wind max coming out and across the southern part. So you almost have like two jets, one much stronger one to the north, but a little weaker one down here to the south too. So it's just something to go back and look at with time here with these. So we'll go back and take a look now. We'll come down another level here. So let's go down to 500 millibars. That's about halfway through the atmosphere. So we should be seeing some of the same features we saw on the jet, but not as strong a winds. Again, there's maybe a little bit more of a frictional influence here. Not much, but a little bit. And might actually pick out some of the lows. But what really you can see right here is, yeah, there's a big low up over Hudson Bay, which is very typical for this time of year, particularly in January and February. It's a little bit further south than normal. But you're finding a very fast east to west flow. And then there's a trough on the eastern part of the United States right in here. So this is kind of where you would expect low pressure to develop and move up through. Might be pushing some cold air down in the eastern part of the U.S. with time. Not a lot happening the further south you get. This is a very tight jet, very many across the northern United States. And you'll notice that the front was hanging right across almost east to west, paralleling this flow right now. So that it's going to take some time to push south if you see this very much the same flow right in here. So let's go back and look down one more level here. We'll go down to 850 millibars. Now you're starting to pick up a lot of more information as far as, oh, maybe where the warm air is coming from or where the cold air is going. We saw that really strong low up over Hudson Bay. Well, there it still is at 850. What we're seeing, though, is some really strong northwest to north winds here pushing the air down, but they very quickly turn to the east. So, but look how cold that is up here. Celsius-wise, it looks like it's almost a minus 30 Celsius, minus 34 Celsius, as a matter of fact. You think about that air temperature at 850 at 5,000 feet, that's some really cold air for this time of year. While contrast down to the south, here's plus 19, plus 25, 21 down in here. So there's some real warm air coming up through the west side of Texas, on up on the eastern side of the Rockies here. So there's going to be some very strong contrast somewhere in here of temperatures. Again, nature doesn't like a contrast of temperatures, so it's going to try to do something about that. It's going to try to mix this area out, maybe by forming a low pressure system, and you can already see one kind of there at 850 coming across. So it's just something interesting to see how it plays out with time, how all this flow will move across here. But you can also see there's really not yet a good feed of moisture. There's some coming in off the Gulf into the southern part of Texas, but really there's not a lot of moisture coming around here. So let's take a look at NOAA's GOES satellite pictures, and we'll just look at the, let's look at infrared. We'll start with that. What you're seeing here is some thunderstorms developing in the infrared here. Some clouds, and probably even some snow up to the north of it. And then some more high clouds down across Texas in that area as well. Let's go back to the next one, and let's go down to the visible satellite. And let's run a loop of that one a minute. Let's see if we can see some things here. All right, visible showing nice low clouds. We were looking at the moisture coming in the southern part of Texas. Well, here it is. It's coming in, but it's being pulled, at least at a lower level even. These look like pretty low clouds down in here. Coming north, it would be interesting to see what the observations are across Arkansas and this part of Texas to see if this is really a low ceiling coming across. And then you can actually see the other front that we were looking at just north of it, moving right across here. And if you were to look closely in here, you'll see that the clouds don't seem to be moving much. The brightness right in here, that's probably snow cover north of, up by Hudson Bay. So it's probably still have a good snowpack up in the north there, where it's minus 30 loft. So it's very cold there. So we'll look at one more thing here. I want to look at a water vapor. Water vapor can do a couple of things for you. It has the ability to pick out where dry spots are. Dry spots are like in here. There's another one darker colored over here. They typically, the driest air comes literally from a jet, probably. If you think about it, the jet's right at the tropopause. So say you're mixing in some stratospheric air. Stratospheric air is very dry. So you're trying to show you where some dry air might be there. Maybe there's a little jet right through here, another one here. It's also a great way to pick up moisture plumes. You can see moisture coming in here, over out off the coast. You can even see a little bit of a shape to it out here. It might be indicating a low pressure system. So just a few things we're beginning to get into now in the weather that we're talking about here. Let's move on a little bit to see where some ceilings are kind of low. And we saw those clouds coming up. Well, guess what? There's some MVFR down in this part of Texas and up into Arkansas. So there were some lower clouds coming up, some moisture coming up off the Gulf down in there. And we already had some indication of that from the satellites. You can see the low clouds also coming in onshore there in the north, where we saw that real strong jet pulling in moisture off the Pacific into this area, probably causing some rising motions. So there's something in there as well. So these are just some of the tools looking at the observations here and all. If we were real curious and wanted to look at it, here's the actual observation for the northern part of Louisiana, and it's broken at 3,000 feet. So you can actually see the height of the clouds. So into Arkansas, this is broken at 2,400 feet, 5 statute miles in haze. So there's some haze down in there as well. So let's move on. We'll move forward a little bit here. Each Weather Service office, and I am going to be Weather Service centric, I'll admit that up front. I know there's a lot of other weather information you can obtain out there, but I'm going to lean towards the National Weather Service just because I know it best. Feel free to share any other websites you'd like as well, and share them with the class. Here is today's enhanced satellite, enhanced severe weather potential. You notice that we saw some thunderstorms, cloud enhancement over Missouri there, and they actually are forecasting an enhanced area of severe weather in there, a slight risk around it as well. So just something to keep in mind if you were flying in that direction today. And here's some maps and models. So let's take a look at out here in the future and see if we can plan a flight maybe for this weekend. So here's the first forecast We've looked at that low going by here. Here's the high bridging down. 36 hours. That high is just so strong. It's just pushing everything all the way down to the Gulf Coast now. And if you want to go back here at 36 hours, there's a little low off the South Carolina coast. Pretty decent low now, developing. And we saw there was a stronger trough in the atmosphere right in this part. It just seemed to be staying there. And that's where this low is developing around. We'll talk about how that happens in the future. But here comes something interesting now at 48 hours. Something's beginning to move out from the Rocky Mountains, probably in one of the jets we were looking at out west. And while you still have that big high pressure there, now you have a weak low developing over Texas here. So your pressure gradient, well, between the two is like this, and this one's rotating counterclockwise, this is rotating clockwise. And guess what? You're going to start picking up the moisture from the Gulf of Mexico. You're actually getting combined influence of the two, with the high and the low had the helping that way. But they don't take it out very far north. You see, that's one of the questions when you're a meteorologist is just how far north is the precip going to go, or how far south is it going to stay? Sometimes it's very hard to move precip north into a very large Arctic high pressure like this one is, which is day 3 here, still coming down. Over 1040 millibar high. So the low takes from Texas, and 3 days later, and a day, 24 hours later, it's going off the Georgia, South Carolina coast. So if you were looking at a flight, say along the East Coast, and this would be 12Z on Sunday morning, you'd have to consider, well, okay, am I going to be able to, if I was taking off from Jacksonville, would the front be to my north or south of me? That's really the first question to be asked, which way the wind direction would be at the surface. Because say the front was to your south, you might have the low back here, you might have some low ceilings on that side of it, but probably not too much convection. But say the front was back to the north, there may be some convection along it now. So you may have to deal with thunderstorms when you're first leaving. And the next question would be, well, say I was flying to Norfolk. I'll take it where I'm going at. Well, then you're going to have to wonder, well, is the precip getting that far north, or is it staying further south? If it gets that far north, it's a good chance because of that cold air. It's probably going to be some snow. So you would have to deal with low ceilings, low visibilities that far north. Or is it going to stay further south, maybe only into the Carolinas, be rain, and not have to deal with any precip up here? It might just be partly cloudy. These are just some of the questions you're going to be asking yourself. And then you think in the wind direction, well, maybe you saw that really strong east-west jet we had. Well, it's probably beginning to buckle a little bit anyways. And you definitely saw some kind of jet moving more to the northeast up here in New England. So maybe if you were coming out of Florida, you might be able to get enough of a lift and maybe move a little bit, help you along there on the jet. Might actually be helpful for a change, moving you to the east and to the northeast at the same time. So it's just things to think about when you're making and planning these flights in the future here. One of the things I did want to look at a little bit is model guidance. We're not going to deal a whole lot into models yet. We'll get a lot more into them later on. And I want you to at least have some understanding of them. So we're going to look at the GFS model, which is one of the more coarser resolution models. We'll take it across North America, Eastern North America. And we're just going to look at let's take a look at a multitude of things here at once, a 4-panel chart. And since we were interested in day 3 to day 4, I'm going to pick a time here and just try to grab one image. This is 72 hours out, so this is 12Z on Sunday. All right. So we're going to start in the northwest, the 200 millibar. Well, you see, we were talking about the very strong wind, and I was talking about how it was east to west earlier. Well, now it's become more a big, big low over the eastern part of Canada. Little dip in it here, helping that high to come down a little bit. A little strong jet down in the south here as well, helping that low, but it's moving the low due to east. Yes, once it gets offshore, it's going to be moving it up further off New England, but right there it's saying it's going to be pushing it out very strong to the east. So let's look at a little bit lower at 500 millibars. Again, we're seeing that same big high, very strong 500 millibar low over eastern Canada, pushing northward there. Probably a very strong low pressure at the surface out in here as well. And a cold front draping down. You can actually see out to the west to a little bit of a ridge over the rock over off the west coast of the United States. And you can see it at the jet stream as well here. So for once, maybe they're getting a little drier air, at least for the moment in time. The other area to look at then is go down here a little bit, and let's look at what they call thicknesses. We're not going to deal too much with them yet, but this gives you a mean sea level pressure in here. I wanted to look at that. Here you have your high coming down. We talked about how that relates, coming down around the backside of this ridge, this big trough here. Here you have the low pressure coming up, and that would be your planning. Well, gee, where is that front now? It's right in here's the low. Really not a well-defined front like you would have sometimes. And most of the precip, it looks like, is on the north side of that front. So that's something to keep in mind, too, so that the lower ceilings, the low clouds, if you're planning this flight, would be to your north. And say you were like me, maybe in being a stupid pilot, you maybe weren't IFR rated, but you thought you could fly into it. How would I get out of it? Well, at this time, if you go westward, you're going to run into worse and worse conditions if you were flying to Norfolk. The further east you go, the better it might be, but unfortunately you have water out there, so it could be a major problem for you. And the final chart here is 850 millibar temperatures. 850 millibar temperatures give a good indication of where the rain snow line is. And I wanted to look at that just to say that, okay, it is cold all the way down into South Carolina. It's below zero at 850. That's about 5,000 feet up. So it is not that far aloft that it's fairly cold. So that's something to think about too. If you're flying and you heading northward, you'd be crossing, have a much colder air. Your atmosphere would be much colder. So just something to think about on your density altitudes would be changing and all as well. I wanted to go back here to just one other thing on these maps because there's something I wanted you to see as far as not just the GFS. We could loop this out. We could see how this changes with time. But let's just go back here. One more thing. And we're going to do it today. One of the things, there's several very high resolution models. And about 10 years ago, in the high resolution model realm, we began to output simulated radars. So we're going to look at the eastern U.S. and we're going to take a simulated radar. And I think we're going to have to go back an hour. So we'll look at this at from the 19Z run. We're going to loop all these. So if you were to take a radar, an actual radar, and look at the radar that on the Kona scale, if this model was perfect, this is what you should see. Model's never perfect. But look how it developed a squall line here and how it's pushing south. We've talked about that enhanced area of severe weather, and here you can see it. Here you can see the precip moving eastward. This is in the middle of the night tonight, and it's still coming on pretty nicely. A good band of precip. And you can actually see a low and good band of precip developing to the north up there across Pennsylvania. You can see the moisture moving up out of the Gulf, how it's coming up. It literally is flowing probably into that circulation that's up here right now. You can see the thunderstorms down off the Gulf of Mexico and how they're dissipating with time. But here you have that storm's really firing up, and this is late at night. Think about it, 4 or 5Z at night. We're talking, 9, 10, 11 o'clock tonight, whatever, even later. You can actually see the pattern looking like a low pressure system, the way that you have it stringed out to the east, up above it, and down to the south, kind of curved. So this is just something that we'll talk about more and we'll look at more with time. If you were planning a flight for tonight, it's a great way to have an idea of where convection might be developing. There are so many models that are now doing this, and this just happens to be one of the better ones. It's called the HRRR. its resolution is down at about 2 to 3 kilometers. And I've seen some higher resolution experimental output from it that's very good. And the fact that it even picks up on a squall line, it even shows you the more intense echoes. If you had to fly through that squall line, it might actually give you an idea of how far north you need to travel to get around it. Uh, these are all different things you have to be aware of when you're flying. And we're developing this as we go along in the meteorology. So I hope you got something out of it this week, and we'll talk to you more next week.